Okay, I would like to thank the organizers for organizing this fantastic workshop and also giving me the chance to speak at the last talk of this entire workshop. So today, as you can see the title, I'm going to mainly talk about how we can probably get more cosmological information from possibly look at the data, look at our cosmic web in a slightly different way to extract them. And I would like to say that this probably is just one version of the story. If you have been listening and watching people's talks carefully, and you'll probably be able to see that this connects to or echo back to some of the talks we've seen on the first day, particularly to Tom's KAN statistics, and also to Istvan's indicator power spectrum, and also further back to some of the work done by Rabi and collaborators early on environmental dependent clustering. Right, so, but let me show you how we get to this point and my version of the story. So, starting from the basics, this is my view of the universe in the early time. We have the CMB, and typically the simplest thing we could do is to look at the PDF of the temperature fluctuation, which is a guide of the underlying potential fluctuation, and it's typically extremely close to Gaussian. And then the universe evolved towards the late time, where we can see the underlying matter fluctuation by these bias traces, which is our galaxies from Sloan. And typically what we see is now something close to a log normal distribution. So that's the kind of the first order, first movement we can do. And in cosmology, quite often we see, we like to do power spectrum. And to my mind, the power spectrum is no more but just the variance of the field as a function of scale. And in a pure Gaussian field, we know that this is complete. It's basically just characterizing the width of the Gaussian as a function of scale. And that works very well. You can see the success of the standard model from the early time. We have the CMB power spectrum, and we fast forward the growth simply by using this growth rate parameter to the late time, and then they match up fairly well with the clustering from galaxy redshift surveys, such as Sloan. But the thing is, the data don't actually stop just at a few tens of megaparsecs here. We know that further down here, there's a lot of clustering as well. But at the same time, we see the deviation of the growth from this simple linear rescaling factor. So in the community, we've been advocating a lot on kind of designing a bigger and deeper surveys to harvest this part of the information, basically the linear regime, where the growth is linear and the field is Gaussian. Therefore, we can simply just use our standard 2-point statistics to extract the information. But on the other hand, you can see by eye that the error bar here continues to shrink down. That means there's a lot more modes to harvest, and there's a lot of information here, but it's the trade-off is getting harder for the modeling. So it is in this context that I think it's at least equally important to try to think harder to extract some more information from even just existing data, because the data is already there. So in this context, of extracting the growth rate parameter, the wheel has been invented by the great Kaiser sitting there, which is using redshift space distortion. So this is one-line equation where in the linear theory, indeed, the redshift space clustering of power spectrum, it can be mapped to the real space version with this growth rate factor there. So therefore, by observing the redshift space distribution of galaxies, then you can use this anisotropic distribution of galaxies to kind of extract the growth rate parameter. So that's has been now a standard exercise for Galaxy Redshift survey, and this start from this is one of the earliest one back in 2001. People use about 0.1 million galaxies from the 2DF Galaxy survey, and they exercise this constraint and obtain some constraint on the growth parameter of order of around 10%. And over a decade later, this is more contemporary, the Sloan-Boss survey, you can look at some of the papers. You find that now we have like factor of 10 increase in the number of galaxies, and almost factor of 100 increase for the volume. And you can then obtain also this growth rate, the combination of f times the sigma a, the growth rate parameter, for several redshift bins. If you look at these numbers, they are better, but it's not as great as we would expect, because given the amount of increase in volume and the number of galaxies. And if you look carefully, it's actually because part of the reason, to my understanding, is that we now have a lot better, a bigger volume, therefore the statistical error is a lot smaller, and that really push the requirement for the accuracy of the modeling to be a lot higher. So in a sense, we as a community, we cannot go any further to these smaller scales where basically a lot of the models would not work. So it's a bit awkward on the one hand that we now have a lot more data. We have actually clustering will continue up here to the sub-megaparsecs level, but because the limitation of the modeling, we cannot access those information. So that is the observational motivation. So we'd like to go back to the basics of on the modeling of redshift space distortion. So basically, the observed distance of a galaxy will be perturbed by the peculiar velocity. And then back in the 80s, people have written down this. This is now the correlation function language. The redshift space correlation function can be mapped to the real space version if we know the full distribution function of the pairwise velocity along the line of sight. So that's, to my understanding, it's exact. But in reality, this is difficult to get from first principle, and therefore Fisher in 1995 say that if we then assume the distribution is Gaussian, then it can be explicitly written down in this form. And what we need then for this mapping is three pieces of information. One is the real space correlation function, and the streaming velocity, and the velocity dispersion. All these are as function of scale, right? So we can see how well this works. So we can then go about to provide all these three pieces of ingredients for the model from simulation, can measure it, and then feed into the right-hand side of the equation and see how it works. So this is, I think, is the prediction versus the model. Is one is in dash, another contour, and one is in solid contour. So you can see that around most of the scales, it looks quite good, but close to the middle, around 10-20 megaparsecs or so, there's some clear deviation, even seen in this 2D correlation function. And this has also been demonstrated earlier, it's known. So basically, all the three ingredients from the model were taken as exact in this kind of idealized thought experiment. So the failure here is basically saying that the Gaussianity, the Gaussian assumption, is not right. Therefore, that motivated us to go to advocate doing split the density. So the idea is, what if we now, at this late time, observed galaxy density field, in the log-normal type of galaxy PDF, we split it up into various of bins, and then we look at if there's any chance that for example, the Gaussian condition can be better matched. So this is an assumption. So the idea is that basically we can go about to look at this complex cyclic web. Instead of doing pair counting, now we firstly throw spheres of a fixed radii of our choice, and we can split them up into, for example, void regions in blue, and intermediate region depth of densities in orange, and high density regions in red, etc., etc. And there's no requirement for how many bins or what radius you can choose. This is up to your choice. So instead of now having one two-point correlation function measurement, you can have a few. So here we have 5. We split them into 5 bins, varying from the lowest density bin to the highest density bin. We call it DS1, 2, 3, 4, 5. So basically, you can consider this blue line as the void galaxy cross-correlation function, and the pink one as the supercluster galaxy cross-correlation function. So immediately, you can see the asymmetry at around the smoothing scale, which is around 50 megaparsecs. So this is basically saying that the density PDF is deviating from Gaussian. Otherwise, they will be symmetric. And if you go to larger scales, you can see they become a lot more symmetric. And that's exactly saying that if we smooth the density field at a much larger scale, then it has to get back to Gaussian because the perturbation is a lot smaller. So another way to see this spectrum of correlation functions is indeed to slice them along at different scales. You basically obtain the PDF of the density at different scales. And it is in this context, I think that this statistic is basically quite connected to the KN that Tom was mentioning on the first day. So let's look at the velocity distribution. So this is showing the velocity distribution at various of the spheres that I've shown you earlier. Now you can see that the histograms of the velocity field from void to increasing densities, this is basically superclusters. They all can be very well fitted by a Gaussian function. You can even see the deviation from the 0 point here. Void has a mean streaming velocity, which is positive. That means it's expanding. And now gradually the peak shift towards negative up to here. The supercluster case is negative, which means it's infall. So it's all kind of correctly being captured. You can even read the skewness of this. They are basically relatively small. And to put you in context, if we compare that to the 2-point, the pairwise velocity distribution, then you can see the skewness is a lot bigger, and also by eye, you won't be able to fit it, obviously, with a Gaussian function. And this is basically the reason why in the conventional 2-point correlation function, the model of a Gaussian streaming model doesn't work very well. So you can also go further to look at the streaming velocity profile. And here I'm again showing the streaming velocity around different density bins. And then the points are the measurement from simulation. This solid line is some sort of slightly beyond a linear model with one free parameter nu here. So if it's everything linear, then nu is 1. And because we know that the coupling between density and velocity in the relatively small scale should not be linear. At some point will deviate from linearity. So, but the striking thing is that by using a simple one free parameter and then exercising the fitting of the 2-point 2-point correlation function in vector space, we were able to capture this profile reasonably well. So this is the void velocity profile, and this is supercluster velocity profile. And in contrast, you can see the dashed lines are the linear version, which is not good enough, but they're certainly not so great for the intermediate bins. But on the other hand, if you look at the 2-point correlation function, you can see that even with the introduction of the free parameter, it won't work very well at below the 20 megaparsecs. I think that's another reason why that the model doesn't work below basically 2 point 20 megaparsecs or so. So then if you feed this in with a template of the real space density correlation function and the coupling between density and velocity, as I mentioned earlier, you can then go about to compare the performance of this model with simulation. So in fact, there's two layers of contours. One is solid and one is dash. One is from the model and the one is from direct measurement from the simulation. And by eye, you can't really see any deviation. It's really exquisite. It's really an excellent agreement. Again, I'm showing in comparison for the two-point correlation function, you see this deviation here. So this is non-trivial because we are all now pushing towards the precision, cosmology, percent level accuracy, and simply this is just not good enough. Right. So far, hopefully I can convince you that by splitting the density, we were able to model the two-point correlation function in vector space to a better accuracy. And now, next thing is by doing this, we also potentially be able to harvest more information, even if we cut off at the same scale, minimum scale for the model fitting. This is the contour, the fitting for some of the parameters. Typically, we do in vector space distortion, comparing the combination of just the lowest density pin plus the highest density pin together versus the green, which is the two-point correlation function, the conventional method, down to the same minimum scale. And you can see by most of the cases, the combination of two-pin density split statistics outperform the conventional two-point statistics by some good amount. And the caveat here is that we still assume that we know the real space two-point correlation function perfectly. And what we're testing here basically is just the density velocity coupling. But so you can also ask where this information comes from. I think it's sort of obvious that the density split, as I show you, at the small scales, it allows you to sample the non-Gaussian nature of the density field. Once that was there, then it basically gives you a bit more information than you have from the two-point correlation function. So there were, after we had that first paper out, there were indeed a lot of questions about where this information comes from, and there's some doubt also about the kind of vector space distortion plus the Alcock-Puczynski joint analysis may suffer from some systematics. So in this analysis, Enrique Paez basically took the abacus simulation and do the most kind of brute force way of Fisher forecast by basically having all the observables measures from simulations of different cosmologies and then take the derivative to obtain the Fisher information. Now it's become probably more clear that in this sense, by doing so, we also have access of information from the real space monopole information. Basically, you can think of this as the full shape analysis. So you can see now the two-point correlation function again is in blue. It's the biggest, and then once you have the density split, even again just two bins, you outperform the two-point correlation function fairly significantly for all of these parameters that I show you. So this is also true for 2D. Maybe this is a bit cliche, but just to demonstrate that in 2D is relevant to, for example, weak lensing or CMB lensing. You want to cast your constraint of the observables on omega m sigma 8 plane. So the conventional way would be CL. Thanks. Basically, it's a projected correlation function or power spectrum that's in black contour here. And yeah, so that's can be being overlaid by other contours. But if you, instead of doing a CL, you can do PDF. This is 2D PDF. But the important thing is if you look at PDFs of a particular smoothing scale, they aren't great. And that, to my understanding, is because by smoothing the field at a particular scale, you are just having one anchoring point for the power spectrum. But if you were able to do multiple smoothing scales, basically you're sampling the PDF at multiple scales. And again, this is back to the 3D version I've explained, and also back to the KNN method. It is basically PDFs of multiple scales combined together that give you exactly the same information as the CL in the Gaussian limit. And I have another, it's not there. There's a log, once you assume that it's not Gaussian, if it's a log normal, then it becomes clear that the combination of the PDFs give you extra information, which unfortunately the slide doesn't show, but if you don't trust me, go to the paper and have a look. So yeah, that would be beneficial also in the context of lensing, if you were able to have PDFs measurements on multiple scales. So far, let's revisit the context of the modeling. So I kind of cheated a little bit earlier in the ratio space distortion analysis by assuming that we know this quantity perfectly, and also the density PDF, which is necessary for the splits. And merely we were just testing the velocity component, basically just a pure RST component, by assuming that we know the density field. So, but this is actually quite doable. There's existing multiple versions of the language that allows you now to fairly accurately predict the density PDF and also the real space density profiles, or what we call the density split clustering, or what Istvan called the indicator power spectrum, or what Ravi will call environmental clustering, the dependent clustering. So this is the situation we're facing. This is the measurement from simulation in real space. So we want to put some model line from the first principle, given the cosmological parameters. Are we able to do this? So the first thing is to have this anchoring point at the smoothing scale, where we can employ, for example, spherical dynamics that have been spelled out by Cora Ullman, etc., and collaborators. The density PDF, this is me reproducing the results, and from simulation is shown in the blue points, and the prediction you can see agrees very well. And this allows us to make a very precise splits. Whichever way we want to split it, we can obtain the estimate of the density at any particular bin, basically. So you can anchor these points at your smoothing scale very accurately. And then the next thing is to think about, well, after we basically throw the top hat spheres on our densities, and then we measure all this whole bunch of cross correlations, what we're actually doing is indeed some sort of conditioned correlation function. We're conditioning ourselves on spheres of different depths. And this is basically what Kaiser and others has spelled out. The Kaiser bias would allow you to do this. And this is also evidenced by, if you take the ratio of the density split or clustering versus the conventional two-point correlation function, you see that this is essentially the bias, and they are all mostly scale independent. So that's strongly indicating that at this smoothing scale, it's almost sufficient just to do linear. So that's what I did. So you can just see that by having the PDF prescription, also some linear prescription of the patch bias, and then you can have a fairly good agreement between your prediction versus the simulation. And this basically allows you to put the model line from first principle. Basically, you can, what I'm requiring here from the model is just to equally slice the PDF and then take the mean and get the bias and put the bias on top of the two-point correlation function, and the agreement seemed reasonably well. So yeah, I just show this slide just to make, again, the connection to some of the earlier work done. And to my understanding now, at the end of the workshop, it's all related. It's all kind of one side of the same story. And this is a great thing. I really enjoy coming to this workshop, realizing that, oh, different people are actually working towards the same thing, but expressed, painted in a different, slightly different language. So I'll just put my summary here. I hope that I convinced you that in the context of redshift space distortion, which is necessary to model the distribution of galaxies that we observe in the real universe, that splitting density allow you to track things down more accurately, and that's because we were able to make satisfaction of the Gaussian condition that allowed the Fisher model to work. And then by doing so, you also were able to extract more information. This is information offered from sampling the non-Gaussian field. And I'll stop here. Thank you.
Just before the questions, a word to John.
We want to thank Claudia here who basically made this whole thing happen. So I just wanted to
Thank you so much. And now the questions.
I'm not sure if I missed this, but did you describe how you determine the splits in the density splits? Because it looks like there's a lot of the PDF space on the right-hand side on the high-density region was like all in one bin, right? So was it supposed to be volumetric or something like that?
Yeah. No, this is a slight illusion because I plot the y-axis in log. If I plot it in linear, it will look basically all the areas between each of the bins should be equal, and that's the only requirement. We don't need to require that actually. This is just for convenience to make sure that the noise properties among different bins are the same.
Boom.
Thanks. Yeah, one curious thing I was wondering as you were speaking, when you showed you were dividing out the 2-point functions and they were all straight lines, you almost wonder, you don't kind of need to measure them. I mean, right? I mean, if you're doing all your pair counts, there's a lot of work to get all of it.
Yeah.
And at the end, all you see is that there's a density offset.
Yeah.
So you can just measure the density. You don't need to do the expensive pair counting, isn't it?
Yeah, that's an interesting point. It's kind of quite related to the question about where this extra information comes from. If this is all just a linear rescaling of the 2-point collection function, then why there is an extra information? And I still think that the asymmetry, basically these lines are not, well, they're sampling in a poorer manner, like basically 5 data points. We use 5 points to sample the non-Gaussian PDF. I think that's at least one source of the extra information we can still obtain. And
right, it just might be the mean density of all those spheres, though, right? That is enough.
Yeah, the mean density of spheres. Basically, that is the PDF.
Exactly,
yeah,
yeah,
exactly. That's why. Yeah, I just saw that from this workshop that this is the same thing as PDFs of multiple scales. Yeah, you're spot on.
Thank you. Just a comment on this question actually is that the bias, the levels, is essentially accruing to the PDF. So the PDF itself has a lot of information with respect to the 2-point function. And then these guys, each of them measure the 2-point function kind of a little bit different way. And as I was showing earlier, some levels are much more linear than other. So for instance, if you just want to extract linear information, you would still want to measure this because you want to go, you want to, from some of them, you can extract more information than others. So the 2-point function, if you measure it, is kind of an unweighted sum of all of these. But with a weighted sum of these guys, you can get a lot more information, and that's why it's first to measure each of them. So for instance, you could weight them with the log, and you can recover the log power spectrum. So the power of this statistic, the indicator functions, is that it has the PDF, which is just the level of each of them, and and then you have the freedom of reweighting your statistic with any kind of information thing in mind. Not to mention that redshift distortions are also much easier. So I think it's definitely should be measured.
But I think Tom was partially asking, do we need to measure it at all R? Was that part?
Yeah, but I think that's my answer, that you should measure them at all R because they all contain information. Like it's, the story is not just that they all, that's the theory, but you have to contrast that with the measurement to extract the information.
All right.
Just while it's passing on, and I think also basically if we don't do the scale dependent, then we're throwing away the full shape information, right? So I guess you need one. This is probably saying maybe for your satisfaction, PDF plus two progression function would be sufficient. Yeah.
So when people do BAO stuff, then the shape of the BAO bump is smeared out, and they try to reconstruct that smearing. So now I'm intrigued by the fact that your low density and your high density plots in the plot that we were looking at until you shifted.
That's a great point. Yeah, actually, it's an ongoing project. We're still looking at the shift. If you calculate it, is easily calculable. It's very small. You won't be able to see it. It's like order of megparsec. So this is we're showing like 100 megparsec. Yeah, you have to be very sensitive eye to be able to see the shift.
I'm not as interested in the shift as if the smear, right? So there's the amplitude of the smearing is changing how smeared the bump is, right, as well as the position of the bump. So the position of the bump doesn't move, right, but the amplitude of the smearing is potentially a measure of the growth factor.
Yeah, absolutely. That's in principle, I would think if you were able to kind of do or choose a correct kernel to smooth your field, you should probably be able to shift to even undo the smearing by kind of splitting it. It's part of related to what Mark Narink and Isvan's earlier work on this pulling the curtain of BAO. They also kind of try different empirical smoothing scales and finding with some sort of smoothing scale, you were able to see the shift better than others. And the shift, I think, is fundamentally related to the smearing.
Christopher.
I guess also a comment, you mentioned one of Cora's paper for the choice of PDF, but 2 years later we also did a split prediction of the Kaiser bias that you expect by splitting into underdense and overdense regions, and it makes a prediction of your previous plot for the in the large deviation limit.
Right. Sure. Yeah. I apologize if I missed out, but yeah.
We didn't split it in 5, and we didn't do redshift distortion, but we did highlight that it's interesting to do correlation functions or tagging. Yeah.
Yeah. I'll add to the.
Prediction for the right function.
Yeah. Yeah. I mean, there's a long list. Yeah. I'll add more points here.
Any more questions? Well, let us thank our final speaker.
But one last thing, we should thank the organizer of the conference for the conference, I guess.
Well, especially Johan.
And specifically Johan, who's been heavy lifting this thing. And those of you who are still around next week, we have a program which is ongoing, and we're looking for a couple of speakers. So if you're interested in presenting your work to the member of the program, Thank you very much for coming and have a good journey back.
Well, thank you very much.